Thanks for joining us.
Hello.
Works? Can you guys see my screen?
Yes, you can see it.
Okay. I think I saw something on the chat. Okay. Hello. Perfect. Very well. So let's continue with our lectures on the let me see how many. So there's so far there's 20 people. Should we wait for anyone else? Might we give them 1 minute or two? In the meantime, if we can wait for some people before we actually begin. If there are any questions from yesterday or the day before, please feel free to ask. And as always, you can just unmute yourself. Or are there any comments? If there's anything you want to share, please don't be shy. I want to see if people are actually paying attention. Okay. Well, if not, we can begin with today's lecture. So yesterday we left off with the Feynman propagator story. And the definition of this guy for the for the theory of the scalar field that we have been dealing with so far is the vacuum expectation value of the time order operators of the vacuum expectation value of two time ordered operators. And if I remember correctly, the last thing I said yesterday was that if you didn't time order, we had the calculation. So here is just a matter of taking what we had found earlier and pasting it here, but with the caveat that if x0 is bigger than y0, then we get d3p 2 pi cubed into minus I px minus y by 2 omega p. And if the time ordering is the opposite, then we just get the same, but replacing x by y. This is our definition of our time order correlation function. And the interesting thing is that there is a way to succinctly write this into a single function without having to note which time was first and which time was second. And that's by introducing another integral. So if you wish to be more explicit, I'm going to do an integral over this dp momentum, dp0 momentum. I add a factor of 2 pi. And then I put in my function, 2 pi cubed And I add, so here, remember these are technically spatial, guys. No, these are the full, sorry. These are the full momentum where P is equal to omega P and P vector. But now here, I leave the same exponential, but now replace P with the P0 integration variable, and I leave the momentum unchanged. And factor of I. So what I'm saying is now you have an extra integral, and if you perform this extra integral, you will get the upper two terms whenever the conditions for the time ordering are satisfied. So if you imagine this integral in P0, let's draw that again. So this is P0, and this is 0. If I expand the denominator will read P0 squared minus omega P squared, right? Because omega P is nothing but the square root of mass squared plus P vector squared. So this denominator has a pole whenever P0 is equal to omega P. So there's going to be a pole at omega P and a pole at minus omega P. So to make this integral well defined, we're going to add a plus I epsilon so that you avoid the pole. That means that now we look at the imaginary P0 components, meaning that we will have a pole right here at omega P minus I epsilon, and a pole right here at minus omega P plus I epsilon. And our integral is going to go through here. Is our integration. But now notice that depending on whether x0 is bigger than y0, I can close this contour. So the term e to the minus I p x minus y contains something that looks like this. So depending on the sign of x0 minus y0, I'm allowed to cross the integral on the upper infinite circle or the lower infinite circle, because it's in that region where this exponential will decrease, and in the opposite region it will increase. So when y0 is bigger than x0, meaning that this term becomes negative, then the positive imaginary part, the negative cancels this negative, positive imaginary P0 times I becomes a negative number, and so the exponential decreases, and you can close the integral from above. And the opposite happens for the condition of x0 bigger than y0. And if you check and you do this integral, you know that each of the contours has only one pole. So each of the contours has one contribution, and each of them will be the contributions that I showed here above. So this is a neat way to write down the Feynman propagator in a single function. And typically you put together the four components of the integration so that you have d4p 2 pi to the fourth, and you get this pole piece, which is also called the propagator on its own, and the exponential factor. Okay, so this is what we call the Feynman propagator. Now, now that we have found this Feynman propagator, let me just do a quick reminder about, well, let me jump into interactions and then go back to the reminder later about normal ordering and time ordering. So now let's move on to the interesting part. Now we will have interactions and we're gonna move away from our free scalar theory. So for the interactions, I'm gonna use a scalar field phi and the complex scalar for as examples, where we have psi, dagger, and psi as our complex scalar fields. So your Lagrangian is going to be equal to your free Lagrangian that we have been working with so far, and a new part that's going to be the interaction term. So interaction terms, you can cook up any term that is not a bilinear, because the bilinears can be can be massaged to go back to the free Lagrangian. So we can think about, for example, 5, 4, 5 to the power 4 interaction. We can have what's called a Yukawa coupling. It's called Yukawa. We can also have a 4, something like the 5-4 interaction, but with the complex field. And we can also have higher order interactions. So 5 to the 6 in this case. Note that I'm using a convention where the coupling, so the strength of this interaction, is given by a coupling. So the lambda, the g, lambda tilde, lambda 6, these different numbers are going to give you the interaction strength of each of these terms. And by convention, they are normalized by a factor equal to the multiplication over fields of the number of fields factorial in that term. So since I have 4 fields in this term, then I get a 4 factorial. I have one of each of the different fields here, so I just get 1 factorial. Here I have 2 complex conjugates and 2 non-complex conjugates, so I have 2 factorial times 2 factorial, that's 4. Here's 6 factorial. So that's gonna be a convention that is handy for later. The other part that is interesting about that we might find interesting when we look at each of these terms is that the action, the units of the action, so I'm using units, are 0 in the sense that it's a unitless number. And if you remember, the action is given by the integral over space of space-time of the Lagrangian. So if the units of x are going to be -1, so in the convention that h is equal to 1, c is equal to 1, this stands is proportional to energy uh, to the -1. So that's why the distances have units of -1 in energy units. Then our Lagrangian has energy units of 4. And from the free terms, so if you remember the free terms in the Lagrangian, you have something like derivative of phi times derivative of phi, meaning that since these derivatives, each of them has a unit of energy, our field itself will have units of energy. And if we look at each of the couplings that I talked about before, then we have that the lambda coupling is unitless, the Yukawa coupling has units of energy, then the lambda 6 has units of minus energy squared. And these different terms get these different types of terms get different names. These are relevant couplings. So for example, the mass term, let me move this a little bit to the right. We have the mass term in our free Lagrangian. And the mass is also a relevant coupling since it's bigger than the energy units bigger than 0. Then the units the unitless couplings are called marginal, and the couplings with negative energy units are called irrelevant. Okay, and why this is the case, or what's the rationale behind these names? Well, if you want to know if a coupling or an interaction is strong, you want to look at the value of the coupling itself. So a strong interaction means.
Felipe, there is a question for you.
Go ahead. Thank you.
It is on the chat.
Okay. It's not a factor related to asymmetry. It's just going to be conventional so that the calculations with the Feynman rules are easy to perform. So it's not asymmetry. It's just conventional for later on the calculation. It has to do with permutation. So it's the amount of terms that each of the I didn't realize I gave permission for other people to use the screen.
So it was my mistake. Please erase that.
No worries. I'm not sure how to erase that though. Give me a second. I can see. I got it. Yeah. So this is just more of a convention that's gonna be handy for how many ways you can have a term. These fields, they have factors of the creation and annihilation operators, and the way that this will be able to annihilate and create particles. You will have 4 factorial times of types of permutation for the same field to create a particle. So to not have to carry around those permutation factors, you divide that factor in the beginning. So going back to the discussion, when you have a strong coupling, that means that you have a coupling constant that's very, very big. And a weak coupling just means that your coupling constant is very small. So what happens with relevant and irrelevant couplings? Well, they are not unitless numbers, so you cannot just say if it's bigger than 1 or smaller than 1 because they have units. If I change the units, then the number itself would change, and then if it was bigger than 1 in one unit system, might be smaller than 1 in another unit system. So instead, you have to form some kind of ratios to understand how strong the coupling, the interaction is going to be. And typically, you can imagine that there's going to be a characteristic energy that can be used to find how strong a coupling or how relevant a coupling is going to be. So you have G over E and lambda 6 times E squared, where E is just a characteristic energy of the process. So at low energies, you can see that this term at low energies, this term is very relevant because it can become arbitrarily big, while this term can become arbitrarily small. So at low energies, relevant terms typically are important and irrelevant terms can be neglected. That's the idea behind the naming. Now I can introduce something that I said I would. That's called effective field theories. And in an effective field theory, instead of taking your standard model fields, you choose the relevant degrees of freedom for your problem. So if you're looking at scattering of pions of nuclei, then you don't really need to know about the details of the quark interactions if in the initial state and the final state you only have nucleons and pions. So you can write a Lagrangian that only depends on nucleon fields and pion fields. And you try to respect, for example, isospin symmetry. The strong interaction has also another symmetry that's called chiral symmetry. I didn't talk about too much, but it has to do with the fact that the masses of the quarks are themselves very small. So if you make them not only equal to each other, but equal to 0, then you gain an extra symmetry called chiral symmetry. So you can imagine that you have the microscopic symmetries and you just apply them to the effective fields, the nucleon and the pion fields. So to form a Lagrangian that respects these symmetries. And then you can add terms that break the symmetries explicitly to take into account that they are not really a symmetry of the real world. And depending on the coupling, these effects can be small. So if the coupling, if we have couplings, well, it's not a function of anything, but big couplings, then strong effects, and vice versa. And typically, when you write these effective field theories, you would write not only terms with relevant couplings, but also terms with irrelevant couplings that will give probably small corrections, but nonetheless are needed to have more accuracy in your calculation. Okay, so that's the main idea of effective field theories. Okay. Are there any questions about that before I go back to some mathematical definitions?
Hi, Felipe.
Yes, go ahead, Ruben.
Is the chiral symmetry, which transformation is transformation of group or
Yep, yeah, it's also a group transformation. So I said that the chiral symmetry is when the masses are equals to 0. So you might imagine that the Lagrangian is basically uh, something like this. Q bar Q, where Q is the up and down quarks. So something I haven't said is that or something that I mentioned a little bit is that these U fields are spinors, or U and D fields are spinors, which have an extra spinors, which have an extra space-time index compared to our scalar fields, which means that in the case of a Lorentz transformation, then a Lorentz T, then we have some representation of the Lorentz group that makes our spinors change. And you would have something like this. So there's this matrix in what's called Dirac space typically. That's what's typically called. So isospin symmetry was a transformation taking Q to RQ, where R was something like e to the I alpha eta sigma A over 2, where these were the Pauli matrices in isospin space. So this is an SU2 in up and down space. Chiral symmetry is a transformation where R, so R chiral, is going to be something like e to the I gamma 5 alpha, where gamma 5 is a matrix in Dirac space. So this transformation doesn't apply for the mass term, but then it can be used for the derivative term. And so this transformation is slightly different than the typical, and then this polymatrix is the same as this one. This transformation is on top of your isospin transformation. And the reason that this doesn't work is that for the mass, is that if you have the mass term, then this is not equal to RCQ dagger RCQ. But because of how this gamma 5 interacts with the delta, with the slash derivative, then Q dagger Q is equal to RCQ. So this is an extra symmetry of your Lagrangian when you have massless quarks.
thank you. Is SU2 symmetry?
Yeah.
Oh,
Yeah, it depends on the number of massless quarks. So if you have only two massless quarks, then you have an SU2 symmetry. For
thank you.
for three massless quarks like UD and Strange being massless, then you also have a SU3.
Thank you, teacher.
Okay. Okay. So how do we take into account interactions mathematically? This is gonna be the next part. So for that, we're gonna use what's called the interaction picture. So yesterday I talked about the Schrödinger picture and the Heisenberg picture of quantum mechanics. So today I'm gonna have another picture. And for that, I'm gonna split my Hamiltonian into a free Hamiltonian that, we can typically solve, we know how to solve, and an interacting Hamiltonian. So if you remember in the Schrödinger picture, we had the Schrödinger equation telling us how our fields evolve, right? We had the Hamiltonian here. And in the case of a free theory, where H0 has no time dependence, then the solution is quite easy, or relatively easy, in that you only get that the Schrödinger is a time above or exponentiated Hamiltonian of the time at 0. So in the interaction picture, we're gonna define a state where we hit it with the free Hamiltonian. We hit the Schrödinger state with the free Hamiltonian. So you have a Schrödinger state that evolves according to the left-hand side of my page, and then we just hit it with this free Hamiltonian operator. If you define that, you might take the Schrödinger equation and look at what this new state evolves like, and you should be able to derive that the Schrödinger equation for this interaction picture becomes the derivative time of our state going to be equal to e to the h t0 h interaction. So this is the Schrödinger Hamiltonian. This is still the Schrödinger Hamiltonian. E minus h t, and this hits this interaction. Sorry, this is the interaction state. So now we see that in this picture, important bit is that in this picture, the driver of the dynamics is only the interacting part of the Hamiltonian, and it's itself something that looks like a Heisenberg operator, but that only evolves with the free part of the Hamiltonian. So that's why we have been spending so much time with the free fields, because in the interaction picture, we only need to take the fields that are part of the interaction Hamiltonian, but only evolve them in time as if the theory was free. So in a sense, what you write is that sorry, so this interacting state evolves with the interacting picture Hamiltonian, where the interacting picture Hamiltonian is the evolution of the interacting part of the Hamiltonian under the free Hamiltonian. So this looks like a Heisenberg operator in the free theory. Okay. And formally, you can define that your state in the interacting picture is going to be given by some unitary transformation from U state at an earlier time. So this is kind of like a formal solution of this equation. So you can, plug this back into the Schrodinger equation to find a Schrodinger equation now for this unitary operator, unitary evolution operator. And, you would get something very similar to before, where this unitary evolution operator satisfies this differential equation with the interacting Hamiltonian multiplying itself. Okay. So if you look at this is a first order differential equation. It should be super easy to solve if you think, if you don't go and think very carefully about it. You might say, oh, well, I can just take an exponential and solve this differential equation. T0 t hi t dt. So what's the problem with trying to solve this differential equation this way? Well, now everything is an operator. And if you wish to expand this exponential formally, then you have something like 1 plus the integral 1 time hi t dt plus, oh, sorry, actually you get the minus I here. So to get to the I here. So you have minus I squared over 2 t0 t, but then you have a second integral dt prime dt double prime hi t hi t double prime. So now a problem arises in that hi of t prime might not necessarily commute with hi of t double prime. Plus dot, dot, dot. So this integral is ill-defined in the sense that I can define it one way, put the ht prime in the left, do the integral, but then if I put the hit prime on the right, then the integrals will give me a different answer because of the commutator, of the fact that they not necessarily commute. And so somebody found the solution to this equation formally, and that's called Dyson's formula. And it's given by the time-ordered exponential. So you take this time ordering instruction and you apply it to this exponential, and this is a good solution to our interacting picture equation. So now in this case, you don't have an ordering ambiguity because the time ordering is going to tell you, well, do the integral up to the point where t double prime is less than t prime in this way, and then when t double prime is bigger than t prime, then invert them and then carry out the rest of the integral. So written down, this would look like the time order t0 has the 1 minus I term, so the linear term, then the minus I squared over 2, and then you get two integrals, t prime. So the integral from t0 to t prime has hi t prime, dt double prime on the left and hit double prime on the right. But then the part from t prime to t of the t double prime integral, then you get the Hamiltonian evaluated at t double prime on the left and the t prime on the right. So that's what our time ordering operator is telling us to do. Okay. And this is a formal solution to the Schrödinger equation, but it's what we're gonna use to calculate perturbatively the um, the interaction between our different fields. So let's make an example. So let's use as our interaction picture the Yukawa interaction. So the Hamiltonian again is the integral over 3 space of our operator. Yes. Did I hear a question?
Use the microphone, I think.
I don't think I hear. Okay. I'm not sure if that was a question or not. I'm gonna continue. Okay, so we're gonna use this Yukawa interaction as an example. So in the Yukawa case, or I remember that now these are the free fields evolving in time, and the free fields, we know that we can write them in terms of creation and annihilation operators. We're gonna use A and A dagger for the phi field. Then we're gonna call these mesons in this toy example. And nucleons are gonna be the phi x is gonna be proportional to B and C dagger. Ladder operators and psi dagger is gonna be proportional to B dagger plus C. So the A dagger creates mesons, the A annihilates mesons, the B dagger creates nucleons, the C dagger creates antinucleons, and so on. So for example, HI is gonna have a term proportional to B dagger, C dagger, A. So I take a dagger from each of the terms, of each of the nucleon terms, and an A from the meson term, which means that this type of interaction will be able to create a nucleon and an antinucleon. But it will annihilate a meson. When I have the interaction squared, and it's gonna come up in the exponential expansion, then you can imagine a term that has the opposite of this. So this type of term will perform the same as before, but then do the opposite. Annihilate the nucleon and antinucleons and then create a meson. So that's the type of terms that we will get from this Yukawa interaction. And to use these terms, what we will need to do is have some final state that we're interested in sorry. So I have some final state that we're interested in, have some initial state plus t minus, have some initial state that we're interested, and then take the limit as t plus goes to infinity and t minus goes to minus infinity. So we have an initial term in the past, we let it evolve, and then become our final state, or see how it overlaps with our final state. And this is what's known as the S matrix, or scattering matrix. So this matrix is going to tell us how any of initial terms that you can cook up are going to relate to any of the final terms that you cook up. So if you have initial two nucleons that interact with each other, how does the final two nucleons coming out of the interaction are going to look like? And because this S is defined in terms of this unitary evolution operator, one of the important properties is that it's a unitary operator, meaning that S dagger S has to be equals to the identity. Okay? And okay. So our goal is going to be to calculate this S matrix to know what is the probability of being from an initial state to a final state. And for that, we're going to have to use the definition of this unitary evolution from the interaction picture, which is that the time order of the unit matrix minus I d4x. So now we can take the integral over all of spacetime because we're taking the limit of time going to minus infinity to infinity of the interacting Hamiltonian density. So one time, and then the term squared, where we have d4x x1, d4x x2, Hamiltonian density interacting x1, Hamiltonian density x2, and so forth. So note that this time I don't have to worry about the ordering of these two terms because the time ordering operator here at the beginning is telling me that whenever one is in front of the other, then whenever x1 0 is bigger than x2 0, then I should leave it like this. But whenever x1 0 is less than x2 0, then I should exchange them. And I can exchange them without the cost of a commutator just because of the definition of the time ordering operator. And so you might think, okay, so we saw that at least we know how to calculate the time ordering vacuum expectation value of two operators, but these interacting Hamiltonians have 4, 6 operators, each of them. So we now have to know how to calculate time ordering of way more fields in order to calculate matrix elements of this S matrix. And so to our rescue comes what's called Wick's theorem. And Wick's theorem basically tells us that the time ordering. Oh, so before I tell you the definition of Wick's theorem, let me remind you of the other type of ordering that we have talked so far. And or before I do that, if there's any questions so far about the definition of the S matrix, this is a good time. Okay. So let me see. Okay. So let's talk about Wick's theorem. So for that, let me first remind you about normal ordering. So in the example of two fields, x1 and x2. So the normal ordering of these two fields would be that when I write them in terms of creation and annihilation operators, so to do that, I have to write down the Fourier decomposition of the fields. So it involves two integrals because I have two fields. But now all the multiplications of the different ladder operators are gonna be given in such a way that all the A daggers appear to the left and all the annihilation operators appear to the right. And each of them comes with their factor of the Fourier transformation. X2. So check that if I haven't done the normal ordering, then P2 that is related to field 2, X2, is related to P2 in the Fourier transform. So the creation, the operator AP2 would have to be to the right because that's where my operator is. And then these AP dagger and AP1 don't commute necessarily, or do not commute actually. We have an equation that tells us what the commutator between them is. But since I'm doing normal ordering, I'm allowed to just put the AP2 dagger to the left by definition of what normal ordering means. So this is our definition of our normal ordering operator. And Wick's theorem, the definition of Wick's theorem is basically that our time-ordered operator, x1, x2, is going to be equal to the normal ordering plus the Feynman, or yeah, the Feynman propagator. So now we know the difference between the normal ordering and the Feynman and the time ordering, and it's given in terms of a Feynman propagator. And remember that when we took the vacuum expectation value, we found that the time ordering expectation value was equal to the Feynman propagator because the expectation value of a normal ordered operator is typically zero. In particular, the expectation value of this operator, where you have the ground state hitting on the right and the left, is always going to be zero. And in general, that's what Wick theorem is. So the theorem tells us that the time order of any string of fields is going to be equal to the normal order string of fields plus the normal ordering of all contractions. And what is a contraction? So a contraction is going to be joining two fields. So if I have, let's say, three fields, then there is going to be three possible contractions. So this is one contraction. Then this is another contraction. And the last contraction would be between fields. Sorry. Fields 2 and 3. And what is a contraction equal to? So when you have two fields getting contracted, no matter how many fields are there in between them, then this is equal to all the fields in between them times the Feynman propagator, sorry, in between the two fields. And remember that a Feynman propagator is time ordered by definition, so it doesn't matter that I moved around one field to get it closer to another field.
Yeah, Felipe,
Yes.
there is a question in the chat asking what is the relationship between this S matrix that you have defined some slides ago
Mm-hmm.
and to these phase shifts that there were lectures on non-relativistic scattering theory, and there they saw that you can express scattering, for example, observable like the phase shift.
Yep.
Is there a relation between these two? This is the question.
Yes. Yes. That's a very good question. So this S matrix, as I said, is unitary. And in principle, your theory is gonna be Lorentz invariant and also Poincare invariant, which means that if you have defined some state with quantum numbers some quantum numbers that have a momentum, a total momentum of the center of mass frame, and some angular momentum and the projection Lm. So something that the theory has to satisfy is that the S matrix has to conserve angular momentum and total momentum. So this can be given in the grounds of conservation quantities, since S is going to be given in terms of your interacting Hamiltonian, and the interacting Hamiltonian itself can conserve, being a Lorentz scalar, has to conserve angular momentum and linear momentum. So we already see that the S matrix has to be diagonal in angular momentum space, and then this infinite dimensional space of momentum too. So something that you can define is that, or you can think, is that this S matrix, if you write it as a literal matrix in Lm space, so Lm goes to here, and Lm prime goes here, then only elements in the diagonal are going to be non-zero. Here you will have 1, 1, 1, 1, 1, 1, 1, 0, 0, and so forth. So it's conventional to just say that S is DL DMM SL. And technically you can have an extra index M, but also by angular momentum conservation, you should find that S cannot depend on M. And since it's diagonal, then each of the individual elements has to be satisfying the unitarity. So this equation has a trivial solution in that SL has to be equal to, can be defined to be equal to e to the I 2 times delta L. So this delta L is what's called the phase shift. So that's the relationship between this phase shift delta and the scattering matrix S.
But my doubt is, my question is, the phase shift can be a experimental parameter. We can measure this in
Yep.
the experiment. And at least in the previous class, we assumed the form of the S-matrix as the exponential of something that depends on the phase shift, and the phase shift is related to the scattering of a wave that comes and interacts with a potential. How do we relate the experimental value of phase shift to this one that you were presented to us? Because I don't know, phase shifts are something very close to the interpretation that we give to the wave, right? We go from
Yeah.
we have
That the boundary conditions of the wave function has to change if there's a potential in between, right?
mm-hmm.
And the shift in that wave phase, it's the wave shift, right? And the name phase shift obviously comes from the non-relativistic interpretation of scattering of particles uh, with potential wells. Then when you do quantum field theory, then you cannot have potential wells because you're trying to explain everything at once. And a potential well is more like an external thing to your theory that somehow was created there. In quantum field theory, we have particles that interact with each other, and then they interact in such a way that it might be equivalent to one particle sitting in the middle and the other particle coming in and technically dropping in the well and coming out. And the point is that you can take this definition I gave you, go to the non-relativistic limit where one of the particles is very heavy, it sits somewhere, it can be represented by a potential well, and you will find that the phase shift that I give the definition here and the phase shift of quantum mechanics there become equivalent.
Okay. So in principle, if we could choose a different representation for the S matrix, here we have this S matrix depending on a parameter delta, but if we chose a different form for this S matrix that respects the unitarity and the previous equation that only the
The
diagonal.
conservation of angular momentum.
Yeah, if we continue to respect these conditions, we could choose, in principle, different representations for the S matrix.
Yeah, that's correct.
Could it be anything else that just it's unitary, but it could be something different than an exponential.
Yeah.
Okay.
Well, technically no, like in the sense that this equation over here, it only has one solution, and it has to be that S is a pure phase, right? If S is has unit, like S is a complex number. If this complex number has unit bigger than one, then this product cannot be equal to one. So this equation already restricts you S to be a complex number of unit one,
Okay.
right? And so the only freedom that you have left is it's the phase. And so we're gonna parameterize it in this way. Why do we parameterize it in this way? Well, technically the solution is because if you go to the non-interacting, in the non-relativistic limit, it becomes the same phase shift that you define in quantum mechanics.
Okay.
For example, that's the reason of this factor of 2 that technically is not necessary. I could have just written e to the I A. But the reason that I have written this factor of 2 is such that when you go to the non-relativistic limit, then you recover that same phase shift that you defined in quantum mechanics.
Okay. Okay, thank you.
Yep. Yeah. Okay. So we get to Wick's theorem, where the contractions are given by Feynman propagators. And let me just directly apply this to a specific problem. So let's say we want to know the scattering of nucleons from each other. So we have this as an initial state of two nucleons and a final state of two nucleons. Which means that our initial state is going to be something like, and this factor is a convention, but we create, we create a nucleon P1 and a nucleon with P2. And our final state, again, some conventional factors, P1 prime, omega P2 prime, where where it's made of two nucleons, P2 prime, P1 prime. So that's gonna be the definition of our initial and final states. So a state of two nucleons in the initial state, a state of two nucleons in the final state. Also, we're typically interested in the non-trivial case. Which is S minus 1. So the one that comes out in S is the case where nothing really happens. Your initial state goes directly to your final state without any real interactions. So we're really actually interested on S minus 1. Okay. So our S matrix in the or S minus 1 matrix in this case has still we're using the Yukawa interaction. So the first order Yukawa term is gonna be 0. So that's a spoiler. And I'm only gonna look at the second order term where you have G squared, dx1, dx2, the time order product of phi 1, psi 1, psi 1, phi 2, psi 2. So I'm reducing the notation a little bit here by writing psi 1 as phi of x1. And when you use weak theorem to calculate P1, P2 prime, S minus 1, P1, P2. So this is our initial final state. So initial was P1, P2. Final state was P2 prime, P1 prime. So Weak's theorem is going to show you that the only non-zero term in this matrix element is going to be equal to the normal ordering of psi 1, psi 2 dagger, psi 1, psi 2, and then the contraction between phi 1, phi 2. So you can do the full derivation, check all the normal orderings, check all the contractions and the normal orderings and see which terms actually become 0 with the commutation relation rules between the creation and annihilation operators. You will find that the only non-zero term is this one. Okay. And an extra simplification is that, or something to be able to simplify this quickly, is that our field acting on a state is just equal to minus IPX. So that means that, so we're gonna call this M for convenience. M is gonna be something like minus IG squared over 2 integral x1, x2. There's gonna be a bunch of exponential terms from acting with the creation annihilation operators on P1 and P2 and P1 prime and P2. So I'm gonna show a few of them so you get an idea of what kind of terms you get. So in this term, for example, you have x1 acting with P1. So it's this. This is not a contraction, but it's really the creation operator acting on this other state. You have x1 on P1, so this one on this one. And then for the second term, you have the x2 with the P2 prime and with the P2. So you can imagine you have x1 with P2 prime, x1 with P2, and other combinations. So we're just gonna leave those as an exercise if you wish. And then the contraction, this contraction is the Feynman propagator between x1 and x2. So I'm gonna call this delta phi. So if you remember, the x dependence in the Feynman propagator is something of the form of an exponential. 1 minus x2. So all the x dependence is inside of exponentials multiplying some momentas. So we can perform so this is d4. The integration over x's, if we remember that this is equal to a Dirac delta. So using this identity, you end up having psi g squared integral of d4k 2 pi to the 4 I 2 pi to the 8. So you have two integrals over x. So you will get two delta Diracs. You have the propagator of the phi particle. So I'm going to put the m phi to remind you that this is the mass of phi in the propagator of phi. And remember that the propagator itself has this integral in d4k. So that's where the integral is coming from. I might as well just write this complete now. And you get the different delta Diracs from the different terms. And so on. So at least one of the deltas is gonna be able to go away through one of the integrations. And you will find that this is equal to I, that's coming from here, minus IG squared. Then each of these Diracs converts K into P1 prime minus P2. For example, P1 prime minus P2 squared minus M phi squared. Then the dot dot dot, I can write this explicitly here now. And I believe me for now that is P1 prime minus M phi squared. and then a final factor of the remaining Dirac delta. Tells you that the sum over PF minus PI. So this Dirac delta is telling you overall momentum conservation. So typically, one defines a new matrix called the scattering amplitude as 2 pi 4, where you take away this overall momentum conservation. So in this case, PF is equal to P1 prime plus P2, and PI is equal to P2 prime, P1 plus P2. And then you have something called typically the scattering amplitude. So we have the S matrix and we have the scattering amplitude matrix, where we stripped away a factor of I, 2 pi 4, and a delta Dirac, the overall momentum conservation from the difference between S and minus 1. Difference between S and the identity. So in this specific case, our scattering amplitude is going to be equal to minus IG squared, and then the two propagators, P1 minus P2 squared minus sin phi squared plus 1 over P1 minus P1 prime squared minus sin phi squared. So these are results, and this is where I want to introduce the Feynman rules. So for the Feynman rules, this is a set of rules that tell you how to calculate AFI. So the first rule is that you have a factor of 1 for each external field. You have a factor of minus IG for each vertex, and the allowed vertex are given by the H interacting. And you have a propagator in momentum space, which means 1 over I over K squared minus M squared for each internal line. And a line. So this is a line. And this is the interaction. So for a case of psi psi goes to psi psi, then you draw a line for the initial state, for each particle in your initial state, and you draw a line for each of the final states. Then the H interacting is going to be given by minus IG P3x phi dagger psi. So it means that you can only have a vertex where you have a phi, a psi, a psi dagger, meaning charge flows in this way, That's the other thing. Charge has to flow for particles that have a charge conservation. So for psi, charge flows in one direction, and then for psi dagger, the charge flows in the opposite direction. So you remember we showed how there's a conservated charge for the psi field. So you have to keep these for conserved charges with an arrow. So now you have to draw vertices like this one in order to join all the lines together. So the only possibility in this case is if you join them together at the center, you put this is not a possibility, for example. No, let me correct myself. This is not a possibility because your vertex has to conserve charge. So instead, the possibility is that you will have the vertex on top, or that the initial state P1 was to P2, P1 prime, and P2 goes to P2 prime, right? So this is P2 prime, 1 prime. So this is, you add up all the possibilities, and employing our Feynman rules, we have two vertices, so we get minus IG squared. In each of them, we have two vertices. Then the internal line, in each case, becomes I. And there's momentum conservation everywhere. So the momentum flowing here, K, has to be P2 minus P1 prime squared minus M phi squared. That's for diagram 1. And then for diagram 2, you have P1 minus P1 prime squared minus M phi squared. And this is the same result that we get using the Weeks theorem. So let me look at another interacting Hamiltonian quickly. Another interacting Hamiltonian that I talked about was lambda prime. So in this case, the vertex factor, the rule about the vertex is that you get a minus I lambda for every vertex. And now your vertex are gonna look like this, where you have the four fields in the Hamiltonian. And again, you have to have momentum conservation for fields that have a momentum conservation at the vector, at the vertex, but also charge conservation for fields that have charge. So the same interaction now has a new first order contribution that is going to be equal to minus I lambda, and that's it. Since for each external field, we only have a factor of 1. Something else that you might encounter are internal bubbles. So in the case of the Yukawa field, or the Yukawa interaction, sorry, you might also have something that has a bubble in the middle. And for these bubbles, you would have to add 1 factor of the propagator for each of them. So now it's the mass of the phi square, K1. So this is K1, this is K2. But by momentum conservation, K1 and K2 are going to be given by the external momenta as well. So you only need to integrate over one of the remaining undetermined momenta. So a fifth rule is going to be integrate over bubbles when not restricted. By momentum conservation. So now when you see a Lagrangian, you're going to see some kind of terms that are not going to be in the free part. And each of these terms is going to give you some vertex that you can add into these pictures to draw new contributions to this scattering amplitude. Okay? So with that, we can finish this part of the lecture, or we can finish these lectures. If you have any questions, now's a good time.
Felipe, the charge conservation for the vertex 2, the diagram, that the X diagram.
Yeah, for this vertex.
For interactive, that I have to choose the charts above, up and down. So right now.
So no, not necessarily. You can rotate this vertex around. As long as you have 2 incoming and 2 outgoing, the charge can be conserved.
So theta have the conjugate charge.
So phi dagger is typically associated with the negative charge and phi with the positive charge. So in here, in a sense, time is evolving in this direction. But then you can imagine, so in this interaction, yeah, sorry, no. In this specific interaction, you would have, sorry, I rushed here a little bit. This type of diagram when you have nucleon antinucleon scattering. Otherwise, this type of interaction, you would have to write 2 incoming, 2 outgoing. Yeah, no, okay. You can also have this equal to minus I lambda because you just move around these arrows. And as long as you have 2 incoming, 2 outgoing, this should be okay. Never mind, this was correct. So it just shows that in this type of interaction, the amplitude between nucleon-antinucleon going to nucleon-antinucleon is exactly the same as nucleon-nucleon to nucleon-nucleon for this toy model. Because these two diagrams are the same, except that I move one arrow to the right and one arrow to the left. But the arrow locations shouldn't be important. What's important is that there are two going in and two going out for the momentum, or for the charge conservation.
There are other or similar diagrams. They have the same result, the same amplitude.
So in principle, you have to add all possible diagrams to a given order. So if you have several diagrams that give the same thing, then you, for the same process, then you have to add them together.
Okay. That's the reason, because factorial.
Yeah, in a sense, the amount of ways that you can rotate these diagrams, you get the factorial terms when you take into account all the possibilities. When you use the Feynman rules, then you forget about. So technically, there was a factor of 4 here in the full Lagrangian. But we normalize the coupling such that in the Feynman rule, then this factor of 4 doesn't appear anymore. Because the ways that you can rearrange this vertex so that technically you can rotate it twice and then it looks exactly the same. Or you can rotate it by 180 degrees and it looks exactly the same. And then exchange two arrows within each other and it looks exactly the same. So that factor of 4 goes away once you take into account all the different ways you can rotate around the diagram, and it looks exactly the same.
Thank you.
Hi, Felipe.
Hello.
Hello. First, I would like to thank for the lectures. I have a question. When you define S minus 1 matrix, I guess, I don't know, when you define S minus 1, we shouldn't have a first order term or not?
So when I say first order term, I mean first order in G, or the coupling. So we're not going to have a zero order term. So S minus 1 is not going to have a term that's independent of the coupling. And that's what you typically call the zero order term. But then there's going to be a first order in G. So G to the power 1. In this interaction, you only have G to the power 2 because of the nature of the interaction. But in this other example, then you have lambda to the power 1 as our leading contribution.
Mm. Okay, okay. Thank you.
Mhm.
So is this the end of your material that you plan to present, Philip?
Yes, this is the end of today's material.
All right, so if there are no other questions, I think we have to thank Felipe for this big effort to present in a concise and very well organized manner this material that will be very useful for the next week. Are you
Thank you.
coming? Are you coming next week? Or
No, I'm sorry, I won't be able to join you guys in person next week.
so anyway, so thank you very much.
Yes.
Hope to meet you soon. Okay. Bye
Yeah.
bye.
It's good. Nice to meet you too, everyone, and hopefully this will be useful for next week classes.
Certainly do. Okay. Thank you.
Bye bye.
Bye bye.